Hello everyone. In this video we are going to talk about two famous methods for going through a graph or graph traversal, basically, which is the process of starting from some node in a graph and then visiting every other node. Okay, it's called graph traversal or graph search. And two well-known methods in general for this graph traversal are breadth first search or BFS and depth first search or DFS. So we're going to look at them and I'm going to explain them to you, and I show you how you can basically apply them in MATLAB, because MATLAB has a toolbox for graph. So these are literally built-in functions, and that's again the power of MATLAB. So what is breadth first search? Here, when you start from some node and you want to go and visit all other nodes, including maybe a goal node, the goal is to visit what we call siblings of the nodes, or the nodes that are at the next level of graph traversal before you're going further down along the graph or the tree or anything that resembles, right? So you want to first visit your neighbors, your siblings, before going and seeing their children and grandchildren and so on. So this BFS has the important thing of it tries to stay as close as possible to the starting node and exploring everything possible before again going down the graph, the tree or anything. One of the applications of it is to find the shortest path in a graph that is not weighted. If the graph is not weighted, means the edges connecting any node to any other node, they all have the same weight, let's say weight of 1, for example, then this method can be used to find the shortest path from node A to node B. And if the edges are weighted, then if you remember in one of my previous videos, we use what? The Dijkstra algorithm. So this is like a simplified version of the Dijkstra algorithm that BFS can provide you. How does this method work? The method uses what we call a queue, and it works based on the principle of first in, first out, or FIFO. What does it mean? It means if you want to visit some neighboring nodes, you put them in a queue, and the first node that you put in the queue in the next level of exploring, that is going to be the first one to explore first. So if something came to the queue first, that one will be explored later first, then the second one, then the third one. Okay, first come, first served, right? Or first in, first out, basically. That's what this method does. This is the pseudocode for it. Okay, now here, let me show you here through this simple graph, and then we solve another example together. So what does it mean, this first in, first out? As I said, if I start at node A, this is the first node I'm going to explore. Once I pass through this node, now I look at my adjacency matrix and see which nodes have a connecting edge to this node A. I found that they are B, C, D, and E. So I'm going to now put those B, C, D, and E into this queue. And now what? Now that I have seen all of the neighboring nodes or siblings of A, now it is time to go to the next level. So this was like level 1. Now I need to go to level 2 and now see the children of this B, C, D, E. But which one do I start with first? With B, because or E actually in this case, right? If you wanted to go with B, C, D, E, then the way that you have to put the Q is like this. The B is put through the Q first, so it comes here. But when the C comes behind it, B has to go 1 unit forward. When D comes, both have to go forward. When E comes, they both have to go, all three of them have to go forward. So since B came first into the queue, now B is going to exit and will be explored first. So now what node is connected to B? That's F. So the next one after B is going to be what? F. B is explored, so now F is going to come to the end of the queue. Then I go to C, C comes out, then D comes out, you see? So the same order they came in, the same order they go out, right? And so I go A, B, C, D, E, and then I go F all the way to whatever you have, and then G, and then H and I, and I go into levels, right? So this is like level 1. This is like level 2, this is like level 3, and so on. Now, not of course always it is this simple in terms of the shape of the graph, okay? Because sometimes the graph could be quite a bit complicated with a lot of cycles and so on. But in general, as long as you follow the process and the order in the queue, you should be fine. So this is the pseudocode, and instead of me reading from the pseudocode for you, which does not add anything to your knowledge, I'm going to apply this pseudocode to this example here. So this is a sample graph. Here I also use some demo code that I have written using the built-in functions in MATLAB for the graph toolbox. And I recreate basically this graph for you. So what you need to pass to it is the starting node and the ending node of each edge. So you go like 9 goes to the starting array, 1 goes to the ending array, 9 goes to the starting, 8 goes to the ending, like 3 goes to the starting, 2 goes to the ending. So here, that's what you see. Then you pass the starting and ending node to the graph. It forms all the edges, and then you can what? You can plot the graph. So here, if I run this section of the code, and if I show it side by side, you see that's the exact same graph, although the shape of it might look a little bit different. But you see this cycle here between 9, 1, 7, 2, and 3, which is here. Then you see the other one between 9, 8, 3, and 4, which is here. And then you see this extra tail branch from 2, 5, and 6, which is there. Okay, so I will also run the MATLAB code after I explain the BFS method. Then you'll see the results are going to be the same. So as I said, we have a queue and we have some nodes to explore. And for each queue, there are 2 operations. There is NQ and DQ. NQ means to add something to the list and from the back side of the queue, and DQ means to get something off of the queue from the front of the list. And what is on the front? The one that you added first, because once you keep adding more and more to the queue, they move from the left to the right. They move from the back of the queue to the front of the queue. So when it's time to take them off, which one comes out first? The one that went in first. So that's why we call FIFO. So let's go over the pseudocode and see exactly what the pseudocode says. So it says the root node, which here we can choose to be 9, start the root node, right, with your graph G. So here we make this guy 9 and add it to the explored list, this root. Here we go, 9. Then what? While Q is not empty, do. So remember, we added node 9 to our explored. We already explored it. Now what? Before you go to your while loop, make sure you add that root to your queue too. So here we push it from the left side in, and now we go through the while loop. While loop says, hey, is your queue empty? You say, no, I have something in it. It says, okay, take it off the list. So bring that node from this side and call it what? node V, the current node, 9. If it's the goal, then return it. But in this case, my basically objective is not to go from 9 to a specific node. My objective is to start at 9 and then explore all other nodes, okay, not a specific target. So for this case, I do not need lines 6, 7, and 8 to be considered at all. So now what? It says from all edges from V to W in adjacency of V. What does it mean? Simple English. It means all of the nodes that are directly connected to what? 9. What are they? They are 1, they are 3, and 8. That's it. These 3, they have direct connections, right? Those are your W now. Explore them. If they are not explored, add them to the explore list. So here we go. 1, 3, and 8. Then what? Add them to your queue. Here we go. Now, how would you add them? 9 was already dequeued here. We took it off, so there is nothing in the list now, but we're going to add this 1, 3, and 8. In which order? So they come like this. The 1 will go into first, then will be shoved forward by 3, then by 8. So it is going to be like 8, 3, and 1. And we have already explored them, so we can add them to this graph here. 1, 3, and 8. They have been explored. They have been added to the queue. And so now it is time to go back to the top of the while loop. Okay, what do I have? Is my list empty? No. Get 1 off. Which one? The one that is the rightmost one, the one that is on the front of the queue. So this time 1 comes off and it becomes the current node here. Again, what is directly connected to 1? Directly connected to 1 is 7. So now I'm gonna add 7 here to my explored list, and it will be shoved into the queue. But again, when it comes, it has to go back to the back of the queue, the left side. So what's going to happen? We push 3 and 8 forward and bring this 7 on the back. Now what's next? Okay, we go back to the queue, and it's not empty, so from the front of it, from the right side, we dequeue 1. So this time the 3 comes off, okay, and you get it off the list, which is here. Is 3 directly attached to something? Yes, 3 is attached to 2 and 4, right? 3 is attached to 2 and 4, as you can see. So we can put them in an order, and we add them to our explored list, and we add them to the queue. In which order? It's up to us, okay? We can start with the smallest number first, then the next number. So now this 2 and 4 come like this. Okay, so this 3 now was attached to what? It was attached to 2, and it was attached to 4. Okay, and if we rearrange this here, 7 and 8 go there, and then 2 and 4 come like this. Then what? Then we go to 8. 8 will be popped off the list, dequeued here. And now we explore 8. Is 8 connected to anything? Well, 8 connected to 9, which you already have, and it is connected to 4. But guess what? 4 is already explored. So it is this connection here that we don't need to go through because 4 is already in my explored list. So this 8 will stop here. I don't need to go any further as a solid connection. I just show it as a dotted line to show that the node was explored, and I don't really need to consider going that path. That's it. So now 8 is over. 8 does not add much other than that dashed connection. Now 7 comes off. And do I have anything for 7? Well, 7, if you look at it, yes, it can go to 2. But guess what? 2 is already there. So it is, again, another what? Another dashed line. It's not going to add anything. So 7 gets out of the current node situation. 2 comes off and will be dequeued. Now what about 2? Hey 2, do you have anything to go down? 2 says yes. I have 3 and 7, but I also have 5. So now 2 goes down, goes to 5. 5 will be added here and will be added at the back of the queue. So now your queue is going to be like 5 and 4. Okay, what's next? 4. It's time for 4 to come off. Let's do it. 4, what do you have? 4 says I'm connected to 3 and 8. They are already there, so 4 is not going to add any value to me. So that's it. Now I'm gonna look at 5, and 5 comes off. Hey 5, do you have any new connection? Yes, that's 6. So now we go to 6. It will be added here and here. And next we go to 6, right? Because 7 is dead end. It's not going to go anywhere. 8 was already dead end. This path from 2 to 5 and 6, this is the active branch. Is there anything after 6? If you bring this 6 off here and take it off the list, DQ that, is 6 going to go anywhere? No. So now this is also a dead end. Plus what? All of my nodes have been explored. So it's over. That's it. Done. Okay, so this is the order of the nodes to be explored. And as you can see, we went this path, but one at a time. We didn't go all the way down from 9 to 1, 7. We first visited 1, 3, and 8, the next level after 9. Then we went down to the next level, which was 7 to 4. There was nothing new from 8. It went to 4, so we explored that level. And when 7 became a dead end and 8 was already a dead end like this, now the only next level that I had was from 2 to going to 5, and then next level going from 5 to 6. So it's like a ripple. It's like when you throw a what? Throw a stone in the lake and it creates this ripple, right? Remember, when you drop a stone in the lake, you have these waves, concentric waves. So these are like different levels that you explore, right? And these are your different nodes of the graph, but not all of them go all the way, right? Some of them will be terminated because they go back to the previously visited. Okay, so this is called BFS. First, explore everything on one level before you pass it to the next level. And this thing that you see here, this is called the spanning tree using BFS. Okay, so now if I show you in MATLAB, all I need to do is to use the command bf search. Could you code it yourself? Absolutely. It's a very simple logic. You can do that. But here I use the built-in function, which, as I said, is available in the graph toolbox. I pass to it my start node 9 and say, hey, give me the list. And it says, sure. What is the order of the Explorer node? It's 9, 1, 3, 8, 7, 2, and 9, 1, 3, 8, 7, 2, 4, 5, and 6. So you see the same order of explore node that we got, you get here in MATLAB as well. Okay, so that was called BF search. Now, as I told you, this method can be used to find the shortest path in an unweighted graph. And here in MATLAB, again, you can use the built-in function shortest path. And I use the same graph. And this time, let's say I want to go from 3 to 6. And so this method can find for me this method of search, not specifically this simple search that we did, but using this strategy, you can find the best path to go from what, 3 to 6, which if you look at it clearly is to go 3 to 5 and 6. So here I pass through the start node, the goal node, and say give me the path, and it says sure. The way to go is to go 3 to 5 and 6, which is of course the shortest way to go from 3 to 6, right? Or let's say you want to go from 8 to 2, right? You go, let's say I want to go from 8 to 2, then call it again. It says the best way is to go 8, 4, 3, 2, right? 8, 4, 3, 2. Of course, it's not good to go 8, 9, 1, 7, 2, because that takes what? That takes 4 edges. This one takes 3 edges. So this command exists in MATLAB, and you can use that. So BFS search and what? Shortest path. Now it's time to look at what? The DFS search. Here it says the opposite of BFS. It says instead of you explore all of the nodes in the same level or all the siblings before you visit down the branch or the children, you do the opposite. You go as deep as you can in one branch until you hit a dead end, then come back and visit the rest. Okay, so get away as much as possible from the starting node and explore as deep as possible in the graph or the tree. This is good when you want to find whether there is a cycle or a loop. And in games that are in applications which are sequential, like games and simulations, where one decision leads to another situation and so on and so forth, this kind of going deep and following the sequence instead of following all possibilities, this is definitely what a scenario to go about, right? So you have some situation here, you take a decision, that takes you to another situation, that takes you to another situation, and so on. So that's what you use in games. And I'll show you the commands here to do DFS search and to find cycles. But how does this method work? Well, instead of the queue, what you have is stack, which is like a vertical queue, and I'll tell you the main difference. And it works based on the idea of last in, first out, LIFO. The operations that you do with the stack, push, and pop are exactly the same as what? NQ, and pop is the DQ. So these are just some new terminologies, and instead of saying a node is explored, you say the node is discovered, right? So none of this is just a major difference, these terminologies. The major difference is this one, last in, first out. And what is the stack and what is last in, first out? So here, if I bring in node 1 and put it in the stack or drop it down the stack, when I bring 2, then I drop it, it's gonna go on the top of 1, 3, drop it, goes on the top of 2, and so on. So it's like a vertical set of things, like for example, a few plates. You consider you have a few plates and you put them like this, correct, on the top of each other. Now, if you have this in your cabinet and there are some new guests and you want to put these plates in front of them, how would you go about it? Are you gonna take this from the bottom of everything else and first put it in front of the first person, or you go with the one that is on the top? Well, of course you go with the one on the top. That needs less work. You're not working against gravity, right? You are not trying to lift everything. So this one that you put last, remember, if you want to put these, how would you do it in your cabinets? You first put the big one in the cabinet, then put the next one on the top, then the next one, then the next one. But when you want to take them off, you first take off the one on the top, then go second one, third one, and then the bottom one. So the first one that came in is gonna be the last one that goes out. LO, last out. Use L. Okay, while in Q, the first one that came in, this guy, it was the first one that came in. It will be shoved forward and it will be the first that is gonna go out. So you see the logic is opposite. What does it mean about the tree here? If I look at the same tree that I had in the previous example, this one, remember I explored all of B, C, D, E before I go to the next level. Here I do the opposite. When I go and visit B, I'm not going to go to C, which is like a sibling of B. I'm going to go down the path of B. So now B after B, I'm going to go F. After F, go H. After H, go C. So instead of me directly going from A to C, I go this path of A, B, F, H, and end up visiting C. Okay, but when I visited C, I'm not going to go forward back to A because that node is already taken care of. It's discovered. So now I look at the other branches and see if there is any chance of what? Exploring some new branches. And what that one needs is something called backtracking. Because when you go down a branch, ultimately that branch is not infinite. Here we are talking about finite graphs or trees. And you have to stop, and then you have to go back on the branch to the place that the branch is connected to the bigger portion of the tree, the trunk of the tree, or maybe to another bigger branch, and see if there is another branch that you haven't discovered. You go down that. If there is not, you go back one more branch and get closer to the trunk or to the root, basically. Right? So you need to do backtracking, while in the BFS search method, you never needed backtracking. If you look at the spanning tree, you see these arrows are always going forward. Okay, now I'll show you in a second that when you do the same thing on the same graph with DFS, at some point you need to go back because you're gonna face a dead end. Okay, so this is the pseudocode for it, this one here. And I'm going to, again, instead of reading it line by line, apply it to this example. So here we have this example. And again, I start with root 9 and start. So it says, let S be the stack. It's empty right now, but now I push my root V, which is 9, into the stack. So I bring that 9 and drop it right on the top of the stack. So it goes all the way down and sits at the bottom. Okay, now it says while the S is not empty, do. So it's not empty. So what should I do? Pop. So you see, push means drop it in, pop means take it off. Take it off from where? From the top of the stack. Right now there is only one thing in the stack. So I just pop this 9 off and just call it V, the current node. So it comes off the list. And then it says, hey, if it's not labeled this 9 as discovered, add it to the discovered. So go. And now that we have added that, let's at the same time draw that spanning tree. So this is 9. Good. Now what? Now let's look at all the edges in the adjacency matrix that connect V to the neighbor's W and push those W's in the stack. So the neighbors to 9 again are 1, 3, and 8. So now this time, let's bring that 1, 3, and 8 and drop them down the stack. So they're gonna go like this. Okay, and now what? Let's go back to the beginning of the while loop. Now the stack is not empty. Pop 1 off. So this time v becomes 1. This 1 comes off. And it's not discovered, labeled as discovered. So I add it as 1. So here we go. That's 1. Go look at adjacents of 1. So that's 7. So now 7 comes and will be dropped on the top of the stack. And we keep going. Again, take the 7 off. You see 7 just came, but now again, it's going to be the first one to be popped off. It will be the new discovered. So it's like this. And 7 is connected to what? Is connected to 2. So 7 was popped off, but now 2 comes and 2 will be dropped here. Go back to the beginning of the while loop. 2 just came, but now you pop it off again and make it the current node. So here we go. It's not discovered, so we add it here as discovered. You see, I'm going deep down this branch. 2 is connected to what? To 3 and 5. Drop them down the stack. So I have 3 and 5. When you drop it, it becomes like this. But now the problem is you have 2 3s. Which one would you keep? You only can keep one of them. You always keep the one that has an upper position. The position of it is above all other replicates. So this 3 is going to go what? Away. Okay, that 3 is going to go away. So your stack becomes like this. And now when you go back to the while loop, now it's time for 3 to come off. So 3 comes off and will be added to the list. So you go here. Then attached to 3, you have what? You have 9 and 4. 9 is already in the discovered list. It's not going to bring a 9 and drop it down here. The only one that is not in the discovered list attached to 3 is 4. So 4 will be dropped down this list. And that's it. Now again, the same 4 comes off and goes there and becomes discovered, and we add it to the spanning tree. So now we go here. What do you have connected to 4? That's only 8. So 8 will be dropped. Again, look, there are 2 replicates of 8. The bottom one will be eliminated. And now that 8 will come off the list too and becomes the current one. It will be discovered. And now 8 has connection to what? To 9. But 9 is already there. Okay, so I'm not going to go from here to here. It is going to be what? It is going to be a dead end. So I go back to my list. 5. Right? Remember, I have a 5. And what does it mean to jump from 8 to 5? You cannot jump from 8 to 5. What do you need to do? From this 8, now that you face the dead end at 9, you go back to 4. From 4, you go back to 3. From 3, you go back to 2. Why? Because when you go back from 8 to 4, is there any branch that you haven't explored at 4? No. When you go back from 4 to 3, was there any branch at 3 that you haven't what? Explored? It was this dash branch, but again, since that one was existing, you're not going to explore that branch. So now you have to backtrack to 2. At 2, did you have something that you haven't explored? Yes, it was 5. is 5. I added it to the list at the adjacent vertex to 2, but I haven't been able to explore it so far because it was what? At the bottom of the stack. So now it's time to go to 5. And you clearly see what am I doing? I'm backtracking from 8 when I faced the dead end. Now I'm backtracking to 4, 3, and 2. And now at 2, I have what? This 5. So I pop up the 5, make it my current what? Node. I add it to the discover list, and I look at the adjacent to 5, which is 6. So 6 will be dropped down here. Again, I go down to 6. This time 6 will pop off, will be added to the explored node. And is there anything to go after 6? No, that's it. It's over. And so what? All nodes are discovered and my spanning tree is complete. So this is how you do the DF search, right? Depth first search. So this is the spanning tree using DFS. And you clearly saw what backtracking means. Whenever you face a dead end, go back to the first branch, to the first node before you, that you can go to a new undiscovered branch. If there is none, go back further. Go back further until you see a new branch that you haven't been to. Then go and explore that one. So this is called what? Depth first search. And clearly in the breadth first search, you'd never see me going back, because I'm exploring all of them at the same time in a parallel mode. So clearly what? I do not need to backtrack. But what do I need? If I don't need to backtrack, it's a great thing, but does it have a disadvantage? Yes, because I'm checking all the possibilities in parallel mode. Guess what? The BFS needs more memory. The BFS needs more memory because you are doing parallel considering and parallel exploring. So always BFS needs more memory than what? DFS. Okay? But it's another way that you explore, and you can go deep and you can get to the loops, right? So when you get to the 3, you see there is a loop. When you go down to 8, you see there is a loop, and so on. Not that with BFS you cannot see the loop, but since you go and you visit one of the previous nodes fast, now sometimes you see with BFS you can explore this 9173 quite fast, or the 9348 quite fast, because the cycles are short cycles and they are all attached to 9. If I started at 5, it took me more time to see what? To see the loops than when I started at 9. So how fast you detect the loops, it depends on where you start. If you want to consider all possibilities, in general, the DFS method is better at detecting the loops faster than what the BFS does. Okay, so it does not need backtracking, but it requires more memory compared to DFS. Okay, so we add this piece of information for you. And here, if I go in MATLAB, the command DFS search can do the same job for me. So here I run it, and you see the order is 917234. Look, 917234, and then 856, and then what? 856. So you see, what I did in OneNote is the same as MATLAB giving me. And can I detect cycles in a graph? Absolutely. There are 2 commands. One is called has cycles, and the answer of it is a logical variable, 0 or 1. So here, if I run that, the answer is 1. Yes, G does have a cycle. But what are the cycles? Here I can use the command all cycles, and it shows you all cycles in G. If I run this one, it shows me what? Let me show you. So it says one loop is 3, 4, 8, 9, which clearly you can see 3, 4, 8, 9. This is this loop here on the left side, right here. This is one. The other one is 91723, right? 17239, which is this one. And then you can combine these two and make it this bigger loop, which is this. Right? Let me clean it up and redraw it here. It's this guy here. Right? 4891723. You can do that one as well. That one is also what? Explored in MATLAB. So there are what? 3 cycles. So I upload this simple code. As I said, it is using the built-in functions in MATLAB, dbf search, dfs search, dbf search, shortest path, has cycle and all cycles, and the command graph. So hopefully this video was useful to you, and I could pass to you the idea of graph traversal using BFS and DFS, and the idea of what spanning tree. Thank you so much. I will see you in my next video.